Hey everybody, this is the 7.3 lesson, which is going to be the first lesson we do in Chapter 7, starting at the place where the lesson's actually the easiest. It actually starts with a quick review of exponentiation and your grade 9 exponent laws. For some reason the notes only give us 3 of them. The product law, what do you do with when you're multiplying together two powers that have the same base? You add their exponents. Let's go over to the one on the right. What do you do when you're dividing two powers that have the same base? What do you do in that case? Well, you would subtract their exponents. You'd be amazed at how many people would say that this is x to the 5. It is not. Think about it. It's 15 x's on top, 15 x's. I'm not even going to write them all. 15 of them divided by 3 x's on the bottom. And that should make sense that when you cancel 3 of them, you still have 12 of them up here. Okay? All right, so let's get rid of that sort of scrap work there. Okay, I can't seem to make it all go away. Haha, there. Okay, next, what happens when you take the power of a power? You multiply them. And that's the 3 basic rules: product, quotient, power of a power. There were a few other rules that you did in grade 9. Let me just get some scrap paper here and take a look at them. Remember, there is such a thing as power of a product. You can distribute an exponent into a product. You can distribute a product into a quotient. This is called power of a quotient rule. And that would be x squared over y squared. You cannot, what you can't do is distribute a power into a sum or a difference. That is not a true statement. Those two things are not the same. Okay, make sure that you understand why. When you square a binomial, of course, you have to actually FOIL it, and what you get is you get x squared, yes, you get y squared, yes, but you also get 2xy in the middle. So this is not a power law. So let's make sure we all understand that. So getting back to the things that are our power laws, there is the power of a product, power of a quotient, and then there's kind of the funky ones you learned in grade, one more in grade 9, x to the 0 is equal to 1, as long as x is not 0. I think that's about it for grade 9. Then you get the 2 fancy ones that you learned in grade 10. You learned that a nth root of x is really the fractional exponent, right? That's what radicals are. Radicals are fractional exponents. And then you also learned that negative powers don't make negative numbers. They make reciprocals. So there we go. That's the 8 rules that we call the power laws. Now, if you haven't done this yet, why don't you pause the video and try to fill this in, see if you can do them all yourself. I just sort of did them beforehand. You should be able to do all of these without a calculator. These should be numbers that you know and recognize. You should also know the rest of your perfect squares. This is kind of too fat. Let me see if I can make it a little skinnier. The rest of your perfect squares, that's better, up to 20 squared. So this thing stops at 5. Oh, no, I'm sorry, it doesn't. It stops at 6. So that's 6, 36, 216, and 1296. Okay, so this thing stops at 6, but you should know 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, up to 20 squared. You should also know any power of 10, right? If they say 10 to the power of, say, 7, you know that that's a 1 with 1, 2, 3, 4, 5, 6, 7 zeros. It's really not hard. So you should know those 2 things as well. So that's everything you should be able to do kind of without a calculator. We will not let you have a calculator for most of the test for this unit. And this is a very important idea. If you have the same base to a power equals the same base to a different power, then those 2 powers must equal each other. So for example, if I have 3 to the power of x plus 2 equals 3 to the power of 7, then we say that x plus 2 must equal 7, and then you just solve that algebraically by minusing 2 from both sides of the equation, and x must be 5. Let's do a check on that. Does 3 to the power of 5 plus 2 make 3 to the power of 7? I believe yes, it does. Can I point out to you that don't make this communication error. I see students make this all the time. I was trying to pick red, but this is obviously not red. But in my fancy rainbow color, this is a mistake. Don't do this. Don't write this down. This is wrong. Students will cancel those 3's and say, oh, therefore it's x plus 2 equals 7. No. This is not a cancel. Think about it. Cancel means, for example, you've divided something by itself. Like I was canceling those x's earlier because it was x divided by x. You've divided something by itself to leave a 1. That's a cancel. When you, say, have the same number on both sides of an equation, you minus a number from itself. That's a cancel. This is not a cancel, okay? Please don't think that it is. It is not, it is not, it is not. This is bad, 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 bad. What you should be thinking is, this statement leads me to this equation. This equation is not the same as that equation, okay? It's a different equation. This equation led me to that equation. I did not simplify this equation, and now it's still the same equation but simplified. That's not true. So please don't write it that way. And let's do some. All right, 2 to the power of x plus 1 equals 32. Well, the only way I'm going to solve this is if 32 is written as a power of 2. So now they have the same base. So now I conclude that this equation, actually some teachers even make their students say therefore, just to make them realize, oh yeah, that's not the same equation. I just made up a new equation based on previous information. So there we go. So x is equal to 4. And then you could check, does 2 to the power of 5 make 32? And yes, yes it does. All right, check out this one. I'm going to have to change my 27 into 3 cubed, but I'm taking that 3 cubed to the power of 2x. So what does that mean? It means that 4x minus 1 has to equal 3 times 2x, which is like saying 4x minus 1 is equal to 6x, minus 4x from both sides, divide both sides by 2, and x is negative a half. Let's check that one. Does 3 to the power of 4 to the negative 1 half times negative 1 half minus 1 equal 27 to the power of 2 times negative 1 half? Well, over here, 4 times negative 1 half is negative 2. Negative 2 minus 1 is negative 3. And remember, we just talked about it. That's 1 over 3 cubed, which is 1/27. Let's see if that's what the left-hand side is. 2 times negative a half is, oh, sorry, that's not a 2. That's a 27. My bad. Ugh. Let's just start that over. There we go. So 2 times negative a half is just negative 1. And yeah, negative 1 makes 1 over 27. So yeah, those two sides are the same. This is the right answer. Yay! All right, they get tougher. This is 3 to the x times 3 to the 3 equals 3 to the 4 to the 2x minus 1. Okay, this tells me, remember that when you're multiplying two powers that have the same base, you add their exponents, and that has to equal that. So let's see, so x plus 3 is equal to 8x minus 4 minus x from both sides, add 4 to both sides, and x is 1. Feel free to run a check on that, but I'm pretty sure we got it. All right, ooh, a radical. So this one's saying 2 to the 2 to the x plus 1 is equal to 2 to the x times 2 to the 1 half. So 2 times x plus 1, that's a, still getting used to this pen. There we go. 2 times x plus 1 is equal to x plus 1 half. So let's see, that's 2x plus 2 is equal to x plus 1 half. So x is equal to 1 half minus 2. I'm going to move over to here. I'm out of room. So that's x is equal to 1 half minus 4 halves. So x is equal to negative 3 halves. And you can, again, run a check on that and see that, yes, indeed, that would be a true statement. Okay, looking at number 5. That's 1 over 3 to the x minus 1 equals 3 to the 4. All right, you know what else I can do with this? I can make this a reciprocal. I can say that this is 3 to the x minus 1 to the negative 1, which equals 3 to the 4. So I can say that negative 1 times x minus 1 is equal to 4. So that's like saying negative x plus 1 is equal to 4. So that's like saying negative x is equal to 3. So x is equal to negative 3. And again, you can run a check on that if you don't believe it. Okay, example 6. Ooh, this is interesting. I am going to just look at it and say, no possible solution. This one's trolling you. It wants you to do a whole bunch of work for no reason. No possible solution for x. Now, how do I know that? How do I know that once I change this to 2 to the 2 and change this to 2 to the 3, that I won't be able to work it out and find a solution for this x? Well, the reason I know all that is because, look at this. There's a reason for this. Let's write the reason out. Let's explain it. No exponent on the positive base of 2 will result in a negative answer. So no matter what this x is, it doesn't matter. There's no possible way it could turn these two bases into a negative answer. It's just not possible, right? Think about what exponents are. They're repeated multiplies. 2 times itself any number of times you want will never equal a negative, ever. But what if it's a negative in there? That doesn't make a negative answer. It makes a reciprocal. Oh, yeah. There is no number of 2's I can times together and get a negative, and that's true for all numbers. There's no number of positives I could times together and end up at a negative. So this one was messing with you. It wanted you to do a whole bunch of work and realized later that, oh, yeah, I can't do that. Okay, we are not quite able to solve equations with different bases, like, say, for example, you had a base of a 10 and a base of a 7. That is coming up later in the course, and that's where we'll stop for today. Next, we'll be moving into graphing. Cool. Thanks for watching.